measurement volume from two different perspectives. So they're actually making two holograms. And in this case, they're recording both, so they're not multiplexing, but they're separately recording at two orthogonal directions and comparing the results. Again, because the inline technique has not got good depth discrimination, the reconstruction of the particle will be localized as X and Y quite neatly, but in the Z direction will be more like a thin thread. So by recording in two orthogonal directions, they managed to overcome that limitation and isolate the location of the particles in a three-dimensional space more accurately. All three of those previous examples rely on the use of holographic film. And as I pointed out, holographic film has very huge resolution and very extensive dynamic range. Again, in the lab of Jokats, Jian Shan, who's up at the University of Minnesota, worked a lot on digital holography, where they basically use inline holography just by passing a laser beam through the measurement volume. And where the recording plane would be, we actually focus a microscope objective. And we magnify the fringe pattern that we could have recorded with holographic film, but we magnify it and project it onto a CCD array, which with the magnification, the CCD array then has enough resolution to record a limited volume. And we use this to look at small aquatic animals and to record the trajectories of small particles. So holography is not limited to holographic film and the necessity for wet development. It can be used with a CCD camera. The limitation being, though, that you're somewhat limited in the total volume or area that you can look at. Clearly, holographic plate has huge capacity to store information compared to even a fairly high resolution CCD. So, I would say the limited resolution of the CCD sensor is overcome by magnification of the inline hologram using a microscope objective. The reconstruction in this case is not done, it's not done optically, it's done digitally within a computer. You can use algorithms to take the stored holographic pattern and then reconstruct it virtually within the computer, and that's what's used in this case. But it's limited to a small volume by the need to magnify the limited resolution of the digital sensor. So holography has the fundamental advantage of micron resolution without limiting measurement depth. And if you combine it with holographic interferometry, you can potentially increase the measurement accuracy to submicron, and even better than particle imaging. However, it requires holographic film and wet development for usable volumes. You have motion shrinkage. You have no immediate preview. You can't just take your hologram and immediately see how well it's doing. You can't then adjust the laser energy and take another one. You have this rather slow turnaround of going to the darkroom, developing, fixing, and trying. And all of these holographic setups have complex optical arrangements, and one particular setup might be suitable for one application, but another suitable for another. So whoever's going to implement it has to have a fairly high degree of skill and experience in evaluating different setups and deciding how best to set up the holographic recording system. The other thing is it's difficult with holographic film to acquire large sample groups to achieve statistical convergence. And if you've got 100 holographic plates, it could take a couple of weeks to go through that and record and develop